Okay, so gradient descent is a general method to deal with an optimization problem. So anything that you want to find the biggest value or the smallest value, you can always use the gradient descent to find such a point. It is sufficient, but there are also some drawback. It is widely used in many places, and one of the most well-known places is the neural network. So for neural network, it is a complicated optimization problem where a mathematician has no idea how to solve that exactly. So there are still some various numerical approach to find the minimum of a certain loss function or cost function where, for the optimization problem. But for today, we are going to use that for the linear regression problem as kind of the startup problems so that we can play with that and have some feeding of it. So it is a method or algorithm, if you prefer, to find the minimum of a function. And of course, if you can find the minimum, you can always find the maximum. You just do the opposite. Okay, so let me give you one of the example to make it more concrete. So let's say we have a function L, and when I write this, it means that it takes two variables, two numbers, and then it generates a new number, which is x squared plus y squared. Okay, so these things, we know that very well that it has a minimum value, which is 0. When x and y are both 0, then this is the smallest quantity that it can reach. Okay, but we are going to view that from a different perspective. Let's try to draw that on the coordinates. Okay, and this is the x coordinates, y coordinates, and you know when here x equal to 1 and y equal to 0, the L value is going to be 1, right? And if it is here x equal to 2, y equal to 0, the L value is going to be 4, and the next place L is going to be 9. And somehow you can draw the line that indicating all the values of L are the same. Okay, and you can also draw this line that indicating that all the values on this line, L is equal to 4. And everything here, every point on this line, the L value is equal to 9. Okay, so I believe you see this picture before. It is basically in the map, right? In a map that you will see this kind of curves, and that it is telling that okay, all the points have the same height at this place. So you can kind of visualize this is a valley, and here is the bottom of the valley. Okay, 就是等高线的意思。Okay, so of course, for this particular one, we know easily here is the minimum, where the minimum happens. When x and y both equal to 0, this is the value of the bottom of the valley, and it is also where the minimum happens. But the computer or us might not know exactly all the time. The function can be complicated and not as simple as this one. And what is the general strategy to find out this quantity? Okay, so before moving on, let's talk about what is gradient. Mathematically, if we have a function, for example, we have a function that sends two numbers to one value, and in this case we will write it as R2 sending to R1. Okay, so it is just a notation. If we have a function like this, and for example, we are sending x and y to x squared plus y squared, and its gradient is denoted by nabla or gradient L. Okay, it's called gradient L. It's upside down triangle, and it is a vector in Rn. Okay, it will has n locations. And what are the entries? The entries are the partial derivative of L with respect to x, partial derivative of L with respect to y, and if you have more variables, then it is the partial derivative of L with respect to each of the variables. Okay, so if you have learned calculus and you should have seen this before, um, and in this case, it is equal to 2x and 2y. It is a vector. But if you haven't done any calculus or you just somehow forgot about that already, we will give you some reason later. But one of the thing is, if you have a function, the gradient is a vector. Okay, so you have a function, then it becomes a vector. And more than that, here is the key that you have to remember, regardless you take any calculus course or not before. Okay, so this is the key. You will occupy all the things here. Okay, what does this gradient L mean? Gradient L is the direction such that along which L will increase most dramatically. Okay, so a few points to emphasize. It is a direction. Okay, it is a direction. And what is this direction? Along this direction, L will increase, and it will increase the most dramatically. Okay, if you follow this line, L will increase. Okay, and because it's so important, let me repeat that in Chinese once more. 就是这个 gradient L， 不管你微积分学的怎样哈，它指的是一个方向。那这个方向呢，告诉你说，你只要沿着这个方向 ，L 就会上升 ，L 就会上升，而且是上升最大的地方，就要从这个 gradient L 的方向。Okay, so really this is the biggest point that you have to take away from today's lesson, and it will be helpful for your future learning about neural network or today's linear regression. Okay, so how does that work? So let's look at one example. So for example, we do -2 and 1, which is about here. Say at x equal to -2, y equal to 1, then we know the gradient L is equal to -4 and 2. Okay, so as I mentioned, this is going to be a direction, and this direction is pointing to -4 and 2, pointing to this direction. And with this map, you should be able to visualize what is the height, what is the slope of all direction. At this point, if you go up or go left, it is going to increase the height. right? But if you go right and go down, you are going to the bottom of the valley. You are decreasing the height. So indeed, this is the gradient of L at this point, and this point tells you that starting from this point, if you go into the direction of gradient L, then you are climbing the mountain. You are increasing the value. So this is gradient L. So the idea of gradient descent is every time you just move to the opposite of the gradient. And depends on your choice, you can move to a certain scalar alpha times gradient L. Okay? And the next time, you will calculate the gradient of the new point, and you can calculate the new gradient and do the moving again. Moving to the opposite direction of the gradient, which is a minus gradient, and you can use some scalar alpha minus certain scalar of the opposite direction, okay? And keep going, then you will go to the end. Okay, so that's the idea of gradient descent. So here is the formal statement. Okay, so the goal is to optimize or to find the minimum of a function L. And this function L maybe have several variables. Let's call that as x. Okay, x as a vector. And what you can do is find or pick a random x. Okay, and if you have a x already, then calculate gradient L at x. And then update x by x minus alpha times the gradient. So it simply says that I'm standing at x. At the next step, I'm going to calculate the direction of going up, but I'm going to the opposite direction, which means I'm going to minus x minus gradient. And you can decide what is alpha. Alpha is the pre-decided hyperparameter, and we call that as the learning rate. And then keep just doing this. So repeat until you feel like it is done. So what happens? There are some things about learning rate you can do. If you do alpha, which is moderate learning rate, like appropriate, then what you are doing is you will drop, and with a reasonable step, it is going to the bottom. But if you choose alpha too small, for example, like 0.00001, then in that case, it is going to the right direction, but way too slow. This is too slow. On the other side, if alpha is too big, what happens is you might overshoot. You shoot to here, and which is good, But the next step, you want to move a lot to the right. You shoot to this direction. And then the next step, you know, okay, you have to move to the left. But alpha is too big. Maybe you move to the left, to the here, and to the right. And it might not converge. So if you realize that your outcome does not converge, then you have to decrease your learning rate. But if you feel like you are wasting too many steps to do the training, then you can increase a lot, increase your learning rate. So it is something that you have to adjust your learning rate. Okay, so that's the main idea of gradient descent. And the key is just always going to the opposite direction of the gradient. And now I want to implement this to the linear regression. Linear regression, let's say we have a matrix. Previously, we called it as x hat, right? And it is m by maybe d plus 1. And we have, we want to train some coefficients, c0 up to cd, so that it is very close to y. Okay. For convenience, I don't want to write the hat all the time. I'm going to write that as a, and I write this as v. Okay, and this is still the y. So we want a times v very close to y. And formally, there is a loss function that depends on the v, and it is a times v minus y, and we want to take the square sum, the norm of that. You can imagine that it is taking the difference of this and then take the square, take the difference of this and then take the square. So this is actually the square sum of the squares. And actually we want the mean of all this square arrow. So this quantity is the mean square arrow. Okay, so for the linear regression, we want to minimize this function, and we usually call that as a loss function. Loss function or cost function. So linear regression want to minimize it. So all you need to know is what is the gradient of L. Okay, so this is going to be a fact. I will supply some reason later, but just take it as a fact. It's much easier for you, probably. So gradient of L at a particular place V is equal to 2 over n a times V minus y times a. And so it is a row vector. This is a row vector, and the whole thing is a row vector. So if you have done some calculus course, you can imagine that this part, if you want to do the derivative of this thing with respect to v, and ignore the fact that v is a vector. So this is kind of a unit, right? This is a unit that's called as u. So you are going to take this, the derivative of u squared with respect to v. So you can apply the chain rule. So it is 2 times u, 2 times u, and then multiply by u prime. And u prime is a. Okay, so that's kind of the way that you can remember it. But somehow just all the time you are writing the algorithm, either ask someone to calculate that for you or just find the solution. Most of the algorithm already have that ready for you. So what you can do is just apply the gradient descent to L, and then you will find the answer. So here is a way that I am going to show you. And indeed, this is part of the homework for the previous group, and it is somehow related to this group because this group have something called the ridge and lasso regression, and it will also use the idea of the gradient descent. So let me show you some of the code that I'm going to do. Let's see. So I'm going to use some of the code from exercise number 3 of linear regression from Scratch, but it doesn't matter. I will copy this part as well. So that's fine. Let me start over. Okay. So this is the setting from the problem, and you can imagine that this is just the setup. Okay, what is the setup? We set up what is the number of sample, which is capital N, and we also set up what is the number of column, which is the d plus 1, which is 3. And this is try to fix the seed. It doesn't matter. Let's try to have a fake data. What is x? What is a? What is v? And what is y? Okay, and our goal is try to minimize 1 over n, times oh, it's here. Okay, minimize the cost function av minus y squared. Okay, and we call that as the loss function. Okay, and somehow I call that cost function. There's no particular reason. If you give me a and v and y, I should be able to calculate this function. So let's say n is equal to the shape, the first coordinates of the shape, and then you simply calculate this quantity. Okay, return the lost. Okay, so 1 over n times np the sum and a dot v minus y, and you have to take the square sum, right? So you can do this. Okay, so you got the cost, and what you can try is you have a and v and y set up. So the cost is about 4.6. At this moment, it is 4.6, and we want to drop the cost. So let's apply the gradient descent. Let's try to run the gradient descent for several rounds, say 100 rounds. And among these 100 rounds, we are going to calculate the gradient. Let's say gradient is equal to 2 over n, right? And times av minus y, this is a row vector, and times a, and that's it. So is equal to 2 over n. N is defined here, so we don't have to do it again. We define here again is because it is inside the function. So we have that, and times a dot v and minus y, all these things. We don't really need to do the transpose. If you do the dot from the left with a, then it is automatically what is the desired thing. So we calculate what is the gradient, and then now update v by v minus alpha times gradient. Okay, so at this point we will need an alpha. Let's set that as 0.1. and update v equal to v minus something. So you can use the shorthand v minus equal to alpha times g. And now we can try a, v, and y, and let's see if the cost is decreasing. So you will see that indeed, by doing this, although I don't really understand the shape or understand how does it look like for this cost function, but we know, as long as we know the gradient, all the time we just update v by the opposite direction, and then the cost function will drop. And it drops in a nice way. You see it drops several steps and then it's just gone. It just becomes 0.78. It is done. So as I mentioned, if you tried say 10, then you will see that it is not going to converge. Okay, when the learning rate is way too large, then it is going to fail. But if you choose a small learning rate, it is still, well, let's try to run it again. It is doing a good job, but stably and slowly. You see, it takes way too long to converge. So finding an appropriate alpha is something that you have to do by the performance. Okay, so far it looks good. Let's clean the output for this cell to run the next one. So let's do that again. And now let's try to print what is v. It looks like this quantity, it is a vector, and because a has 3 is 100 by 3, right? So v stands for C0, C1, and C2. And it looks like in the end, the v that minimizes the L value, the loss function, is these 3 values. But we also know that we can calculate that by the following formula, which is the projection. We can do ATA inverse. ATA inverse, you know what I mean, right? ATA inverse times A times Y is also the minimum. It is supposed to be the minimum. And let's see in this case if it is the same. Linear algebra dot inverse A dot t dot A, and after that dot A dot Y. Here is A dot T. Yeah. Okay, so once you have the correct formula and it's easy to implement the real solution, and this is the mathematically we find exactly the minimum, the solution. But you can also approximate this quantity by the gradient descent, and you can see the performance is not so bad. Basically, you barely tell the difference between them. So this is the idea of gradient descent, and I will copy that to the Discord. Okay, and also here. So you can play with that. The last few minutes, if you are interested in what's going on for the gradient and you want to know how to calculate the gradient, you can stay here and I will spend maybe 5 minutes to tell you how to derive this formula. But if you feel like it's okay that you don't know the details, and feel free to just ignore this part. Okay, so this is the last part of today. Y gradient of L is equal to n over 2 a v minus y times a, when L is this mean square error. You can just apply all the calculus technique you learned. You should be able to find it out. Here I provide you a different point of view. Really, gradient is talking about when you move a little bit and how much it is going to change. So let's say we are going to move to the direction D, just a direction. We don't know what it is yet. Direction. Okay, so t is just a small number that we are going to change all the time. So what we are going to do is start with v and change to a different direction, but with v plus t times d. Okay, we are going to the direction of d and just going a little bit to this direction. And we are trying to calculate the function L of v and L of v plus t plus d, L of v plus td. We want to see the difference. Okay, so the change rate, if I go in along the d direction, the change rate is going to be this difference divided by how much I move, right? If I move a little bit and then it increases a lot, then it means the change rate is a lot. And in the end, this is how calculus work. We want to make t very close to 0. It means that we go to this direction just a little bit, how much it will change. Okay, what is the ratio it will change. And so the rest of that is just simply the calculation. And remember, keep the limit sign, otherwise your calculus teacher will take some points off from you. And then put this formula in. Okay? So we have nt as the denominator and then this quantity. Okay, so we want av plus td minus y square minus av minus y square. And you will see that all of them has av minus y. So let's set u vector as av minus y. Okay. So this quantity will becomes the same thing we had before, and this one will becomes well, let me do the calculation first. This is some calculation you can do. The first term can be expanded by two parts. It is u plus td, the square. So it is going to be the u length square plus 2 times the inner product of u and td, and plus td square. And somehow you can take some t outside. It is 2 times t and u inner product with d. And the last one you can take out t square from the square. The second one is easy, right? AV minus y square is simply equal to u square. So when you take the difference, only this part remains. And we are able to do the calculation further. mt, and then 2t u d plus t squared d squared. It looks ugly, but t and t can be cancelled from the numerator and the denominator. So the first one becomes 2 over n u and d. And let me expand u this moment. It is almost done. U is AV minus y and the inner product with d. And plus t d squared. But when t goes to 0, the last term will disappear. So everything, and this one, you see there is a t, and t is going to be 0, then it just disappeared because it was a squared term, so it is gone. So all the thing remains. The derivative is going to be, the directional derivative is equal to AV minus y inner product with d. Which means if you go in along with this d direction, and the change rate is going to be this quantity, and you can write it in a different way. Oh, I'm sorry, here is a times td. Not to change. And here, sorry, give me some time. So it actually doesn't change the things, it is changing the part here only, AD. Did I miss any part? Okay, so it is AD here. And you can write it as n over 2 times the AV minus y as the raw vector times A times D. So if you're going along with the D direction, this part is the derivative. And this is the row vector, this is the column vector. When D is of the same direction as here, this quantity will increase the most. So this one is the gradient. Okay, so I will stop here.